While driving down the highway, have you ever thought how much gas it takes to transport the goods in tractor trailers like the one behind me? The stuff that we use every day. Well, you know, they've done a lot to the aerodynamics to improve the gas mileage, but is it enough? I recently visited a customer who's using SOLIDWORKS Flow Simulation. In fact, he's an industrial designer himself. He's working with a former drag car racer and improving the aerodynamics of some future trucks that you might see on the highway in the near future. So let's go take a look at what he has to say. Hi, I'm Joe Gallier of SOLIDWORKS. I'm here with Jeremy Singley, and he's an industrial designer who is working on improving what a tractor-trailer, the aerodynamics of a tractor-trailer. And so maybe you want to give us a little bit of background on how you got into starting this project.
Okay. About 2.5 years ago, I think, I got a call from Bob Sliwa, who was creating a company called AirFlow Truck in East Hartford, Connecticut. Bob's a former truck driver and drag racer.
Okay.
And he had, back in the mid-'80s, he had taken his rig, which was I think a Peterbilt cab-over truck, and added a number of aerodynamic features and in an attempt to see what kind of mileage you could get by reducing drag. The drag on a tractor-trailer truck takes up more than half the fuel, overcoming that drag on the freeway. And he got that truck to give him, on his best run, I think something like 9.3 miles per gallon.
And that's really expert type of driving, right?
A lot of that was due to driving, the best driving practices, absolutely.
Okay.
Yep. And I believe that was, in Kansas somewhere on a flat road all the way.
Okay.
So he subsequently did a number of other things in his life, and finally, a few years ago, decided he wanted to give it another try with some more advanced technology and some better aero. And so this way we were able to put a little science into the project and see if we were on the right track without having to build truck after truck and see what works and what doesn't. And that's where we're at now.
Well, let me ask a few other questions. So your background, as I mentioned, is in industrial design, and you've never done anything like this before, have you?
No.
What are some things that you do typically?
As an industrial designer, product designer, which means anything anybody wants designed as far as the enclosure, the interface, how it looks, how it feels, how it sounds. I've done lighting, furniture, vacuum cleaners, farm equipment, anything you can imagine.
Right. Well, you had training on the flow simulation software at our corporate office in Concord, right?
Right, it was a 2-day class.
2-day class. And that gave you all the essential things that you needed to get started with the software?
Yeah, I was very pleasantly surprised because I was assuming that it would be like learning PhotoWorks,
right,
which I use a lot. I'm considered a PhotoWorks guru, but I still struggle with that program after 5 years. It's just, it's difficult to learn, and I thought it would be the same kind of thing. But after the 2 days of training, I was ready to go. I was flying.
All right. So then what you did in flow simulation on your project is we have this model here, right? This model of a tractor trailer.
Conventional, what they call a streamlined tractor trailer truck these days. Yep.
Yep. So it has the, what do you call this? The scoop or?
A cowl.
Cowl. Yeah. So right. So it's very aerodynamic. Now, what did you do with this then? With this model? What
I did, the grant paid for me to have this scanned. Scanned as a
3D model.
3D model.
Okay.
And the company actually did some of the modeling so that I got an Hydras part, and then I did some more work on it. And that gave me a baseline vehicle to put into FlowWorks to see what we were starting with, what we were comparing to, and because the a lot of research has been done on these vehicles. There's a lot of numbers I can pull from the web.
Right.
Even wind tunnel illustrations showing turbulence, where it is. I can learn the coefficient of drag. And so what I did, actually, I did my first flow modeling on the model, on the conventional truck, and generated a coefficient of drag to see if FlowWorks was giving me an accurate read and if I was doing my homework right. And we got a number very close. So we knew we were good to go. But from there on, I could make changes to it as FlowWorks showed me certain hot spots that we needed to, that it might be a good idea.
So you're able to take a look at, were you looking at flow trajectories primarily for how it would move around it and then sculpt it based on that?
Yeah, I'd bring up the ISO lines, and one thing we learned very quickly was it's all about back here.
Yeah,
You know,
okay.
you've got
Right.
the door open. It's all about the back where the vacuum forms.
Right.
And again, this is, I mean, we're not breaking totally new ground here. People have been working on this for quite a while. So there are a number of devices that get added. In fact, this model has some skirts.
Yep. Along here.
Between the wheels. But also back here, behind this cowl, which we call that the gap between the front of the trailer and the back of the cab. That just turned into a hurricane. But the big one, of course, is the huge vacuum that forms behind the trailer.
Right, and as it comes off here,
you just see a huge vortex back there.
You have the air coming from the bottom, but also on the top, and it just huge vortices. And we'll show some pictures on that on the screen.
Yep. So the solution to that is called a boat tail, where an actual part is added back here to take up some of that vacuum. And these are things that people have been working with for years. So you might occasionally see somebody going down the road with some kind of a big balloon on the back of their truck, and that's what that's all about. So we're just trying to optimize that and blend it all into one. It's all been done piecemeal up to this point. It's just blended into one idea that gives us a flow over the whole vehicle. The Super Truck is actually a real truck right now being built on this platform.
Right.
So once we get what we think is the optimal, the shapes for the three trucks, I'll go back and look at them again and go, what you need to do is keep lengthening the rear portion of your boundary until you don't see any change, and then you know you've got all the turbulence in your calculation.
Right.
So I'll do that when we're pretty close to the end.
Okay.
Get real numbers. These are comparative numbers, and they're pretty. I'm sure they're close.
Right. Well, you showed that in the.
That's true.
This model, it came very close to the real number. So we have, again, the current design.
Yep.
You called the Super Truck, and then the Future Truck.
Future Truck.
All right.
Yep.
So how about we go inside and take a look at some of the stuff you've done.
Okay.
All right. So here's the original geometry that Jeremy looked at. That was the scanned model from that toy truck model. So what we'll do is we'll take a look at some of the results in Flow for this, and then how that was set up. So what I'll do first is make this a little bit transparent so we can see the pressures on the body itself. So here's the pressures on the truck, and you can see all the flat parts of the truck that are exposed to the direct air, like in the front here, up along the corners, and even in the wheels in the back there, have the highest pressure. Take a look and rotate this around the back side. You can see some lower pressures here, and we can go ahead and we can probe, pressures wherever we want. All right, and so this gives a nice picture of the differences in the pressures from the highest pressure to the lowest pressure there, perhaps in the back. Well, that's not the lowest pressure, but where a low pressure region is. All right, we can also show. Let's take a look at the front of the truck here. You can see some of the low pressure areas around the sides here. If I increase this a little bit, it become a little bit clearer. Very nicely. I like that functionality in Flow, being able to do that. And I can show the flow trajectories showing velocities on top of this. So let's do that. Showing these two values here on the same plot is something new in the 2011 version that I'm using here. So velocity for the flow trajectories and pressures on the surfaces of the truck. Let's rotate this model. So you can see the velocities moving across here along the truck. And if we look at a side view, let's hide this one and zoom in to the region between the cab of the truck and the trailer. And you can see this torrent, the hurricane of air that Jeremy was mentioning earlier. Now if we focus on the back of the truck and zoom in on that, you can see the flow coming along the top and along the bottom, and creating a low pressure zone in the back here, causing this velocity to be moving like that, this oscillating, recirculating flow there. It can become also clear if we take a look at the cut plot. So let's take a look and show that now. So first I'm going to hide these flow trajectories. So here we see the cut plot showing the velocity vectors on top of that, and the low pressure. These are all colored by pressure, both on the surface of the truck and on that slice through the middle of the truck. And by redoing the numbers on the chart here, we can see that low pressure region a lot better here, and we can probe that as well on the cut plot. Alright, so those are nice little images here. Gives us a nice visual picture of what's going on. But you can also look at, from your goals, what your coefficient of drag is. So let's take a look at how we set this problem up and what was a mesh that was able to calculate these values. So if we go through the setup here, we have our computational domain. This is where the calculation is being computed. So you can see that we have it quite large in the back. Take a look from the front. We give enough room on the sides as well as the top as well. All right, but the back is the most important region. That's where all the wake, and the larger that it is, the more computation you have to do. So you need to take care of that when you're doing the mesh. Here's a cut plot of the mesh for the entire domain, and as you can see further out, you have larger cell sizes. Then by the truck, we've used some local mesh controls, so local initial mesh here, around the truck. And we did this by creating some geometry around it. So let me just show that. And this is you can see this transparent box that was extruded around there. And you can, in the Flow software, under the component control, you can make these local mesh. Disabling that allows flow to move through it. It doesn't see it as a solid. But you can use that then to define some local mesh control. So that's what we've done here. Additionally, if we hide the geometry, you can see the mesh being refined just around the truck, and that's due to an adaptive meshing technique that you can also incorporate into the Flow software. So it captures all the small, fine little details in the flow. After a number of iterations have been run, it captures the velocity and pressure gradients. And if you're doing a thermal calculation as well, it'll capture the temperature gradients. So you can see how we're able to capture these areas where it's very crucial. So it's done a nice job in doing the meshing here for this model. All right, we have in the setup of the problem, when going through the setup, we go through a wizard to do that. And in the general settings, we have where we put in the velocity of the air moving in it, just as if it was going through in a wind tunnel. The temperature of the air and the pressure and the ambient, so we can set it like that very easily. We have some boundary conditions. Boundary conditions are very easy to set in SOLIDWORKS Flow Simulation. You can define, these are typically if you do an internal flow, mass flow, volume flow, velocity, pressure boundary conditions, or moving walls. And in this case, we have some moving walls. We have the ground, which is going to simulate the road moving underneath the truck. So we specify a face, which right now I have the geometry hidden, but we put in that minus 65 miles per hour there. Then we have the wheels rotating. And you can see we selected the wheels, defined a coordinate system for the axis, and put in the rotational speed of that, which you can calculate based on the diameter of the wheel as well as the speed that it's moving in a linear direction. So we've done that for all these wheels, each and every set of those. Alright? And then we put in our goals. We have the first three here, X and Z component of force in the global. So these are global goals. Those are used for convergence criteria, as well as the max velocity globally that's used for convergence control. Now, for calculating the coefficient of drag here as an equation goal, what we need to do is find out what the force in the x direction that is moving the against the truck. So we select it like that. So these are surface goals. And then we can edit and show you the equation goal for calculating the coefficient of drag. So this is twice because it comes from this dynamic pressure 1/2 rho. So this is the density of air divided by gravity. And then we have v squared. So this is the velocity in feet per second. And then the surface area, the frontal surface area of the truck. So that's very easy. You can set up that calculation for you. And that calculates the coefficient of drag, which we mentioned was closely matched with this model here for the real one. If you wanted to start this problem and maybe change some of the geometry to see how that affects the results, you can do that very easily by cloning the project. Let's take a look at an overview of the results that Jeremy had calculated. So this is again the original design showing the flow trajectories. Here's an iteration that he had worked on with some of the boat tail and the skirts along the bottom, as well as closing up the gap in between there. He did some more refining, adding some curvature there, and continually modifying this. Here in the skirt, raising it up a little bit, so that when in his final design for the super truck, as you can see here, they were able to reduce from that original model 60% of the drag, and that translates into about 30% better mileage. So here's the first iteration of the super truck built on that truck platform, and then in the future, for the future truck coming out later, they're going to break all the boundaries, not having to deal with a given platform, able to play with the positioning of the tires and other things that they weren't able to do on the existing platform. So there's going to be more information on that. Their website, if you're interested in that, is airflowtruck.com. You see a picture of that super truck, as they call it. You can find out a little bit more about them, even look at some build pictures. So I encourage you to, if you're interested in that, go ahead and take a look at their website for more. All right. Thank you, and I hope you enjoyed this presentation.